Current satellite systems are expensive and inflexible to operate in a cluster and to cover larger areas in short revisit times. The solution here is a network of many nano-satellites that allows each satellite to share large volumes of data. In this way, information can be exchanged worldwide at any time. The cooperative nano-satellites of the SNED mission are supporting this vision to come true. The SNED mission was initiated by the Technical University Berlin.
6, outside 5, weather boat, start.
Houston now controlling the flight of Atlantis.
Roger, roll, ready.
Atlantis in control.
4 nano-satellites, each weighing 8 kilograms, will be launched into space together with a larger mission in 2018 to fulfill various communication tasks. This way, the transport of several satellites into the low Earth orbit can take place as a convenient piggyback procedure. It involves equipping a launch vehicle with special ejection containers developed by the small and medium-sized enterprise Astro- und Feinwerktechnik from Berlin. Passenger seats of this kind are popular in the aerospace sector as they give even smaller missions convenient access to space. The first container will open at an altitude of 650 kilometers above the Earth's surface, where it will deposit its first cube-shaped passenger with an edge length of just 24 centimeters. The next 3 satellites will then be released in intervals of 10 seconds and start operating immediately. Developed within a joint project by the TU Berlin and the company IQ Wireless, the S-Link radio transceiver is the project's core. It uses S-band frequency to establish a data connection to the next satellite and to transfer information at a rate of 100 kilobits per second, and thus creating a data network among the satellites. The distances between the satellites can reach up to 400 kilometers before exceeding the range limit of the individual transceivers. The satellites remain in sun-synchronous orbit, which enables the swarm to pass over the ground station at TU Berlin. During ground station contact, the data collected from the swarm can be sent down to Earth by S-band connection at a data rate of 1 megabit per second. At the same time, instructions and tasks can be transmitted to the swarm by 100 kilobit per second uplink. Once one satellite is within communication range with the ground station, the entire swarm could be reached via inter-satellite communication. A second ground station installed at the German Center for Satellite Communications, DESC, in Backnang, can use an additional UHF link to collect satellite housekeeping data. Thereby, visitors and student groups will be introduced to the operating mode of satellite systems and to experience the complexity of such systems by participating at a real-time satellite operation in the center's showroom. Although the satellites are extremely small and do not have a built-in propulsion system, their attitudes can be changed via command from a ground operator. This is done by so-called reaction wheels, acting as an angular momentum exchange device. Many applications and services in everyday life rely on an intelligent, satellite-supported communication infrastructure. This kind of small satellite network enables applications within the field of environmental, climate and atmospheric research, which could be used in early warning systems or in disaster monitoring and management. The option of launching and operating extremely small and nevertheless agile, high-performance data collectors and networkers at increasingly low cost opens the door to